All right, I understand the most urgent thing for you will be the written test. However, please notice that assignment number 3 has been released. That's actually going to be what your programming test number 2 is going to cover, which is not that late, right? So you really want to make sure plenty of time to really struggle through assignment number 3. It's more at a different level compared with assignment number 2. You don't just have to program in simply linked list, but also tree and also recursion, everything together, right? You really want to start assignment number 3 as soon as you can and reach out to me if you got any trouble understanding what's going on. It's not an easy assignment, right? It definitely requires some time to struggle through. And for your written test, it's going to be next Thursday, all right, for you guys as well, the same time like a programming test. You can look at the guide that I just released and also for the coverage. So whatever I covered today is also going to be covered for the written test. Some example question, I will make them available on the e-class together with solution by the end of tomorrow, so you can still give a try. And then I'll reach out to you guys about some maybe review session, optional, over Zoom. If that might be helpful, you can join and ask your questions. I'll reach out to you. It's going to be combined with section Z as well. And the makeup lecture for your programming test number 1 about ADTs and stacks. So this lecture here will also be covered in the written test. So you haven't really studied that yet, you want to catch up as soon as you can. We've got lecture template, office hour, TA contact, all the same. All right, you can just get the help that you deserve, whatever you need. All right, any questions? All right, assuming all good. Let's now recap what we said on Tuesday very quickly, and then we're going to move on to today's topic. So last time we actually started with the recursive definition for trees, and you should want to pay more attention to when you got an way too big tree already, in which case you cannot solve the problem right away. So you really have to take advantage of the fact that the structure for the tree is recursive. So this is really something you will have to get used to for assignment number 3 and 4, right? That's really how the assignment has been designed to really help you understand this. So every node has the same structure. So how deep you should really go down to the tree, it really depends on how big the tree is. So you can only do that recursively. Okay? That's the more natural way of thinking. Right? So pay more attention to how the recurring pattern can be identified in the tree. And of course, once we get to the binary tree, it just is like a special case. You only got 2 child nodes for each node, maximum. All right, and then we got the notion about order versus unordered trees. For example, binary tree is an ordered tree. We got left and the right. And left always comes before the right. And we got this generic clause over here about the tree node, right? That's something we spoke about last time. And we spoke about how you can initialize the generic array in this particular case, right? We actually spoke about 2 different cases, and you should really know about the details of what we discussed last time. But recording is there. You can take a look. Okay. And we talk about some JUnit test case where you're shown how you can construct a tree, like a simple 3-node tree over here. You got a root, which you got 2 child nodes. And for each child node, they don't have any further child nodes. So the tree structure stops there. And for assignment number 3, you can look at under the JUnit test package. So there is one class over there showing to you how you can initialize a tree structure using the node class and SLL class given to you. Okay, so that's something you want to look into to really get before you get started with the problems themselves. All right, and then we spoke about how you can compute the depth recursively. This is something we have to revisit again today, but not really to compute depth recursively anymore. But at least you got to understand how you can use the depth to divide the tree nodes into different levels. That's something we got to focus on about the mathematical properties for binary tree. All right, so we spoke about how you can trace it using unfolding. All right, and the exercise I want you guys to try will be how to trace the heights. Okay, so if you go to the lecture site, I already posted some solution for you. Right, if you go to the lecture site, just go under the tree topic over here, and then you will see exercise right here. Right, computing heights recursively in Java. So I would suggest go over the Java code right here. It's also in the lecture site. The code is made available to you. Take a look at the code structure here. Take a look at the JUnit test cases. Try to trace maybe this particular one using the unfolding technique that we spoke about last time. And the only thing I want to mention, right? So there is like a deliberate typo over there, just to kind of trigger you to kind of question. So whenever we talk about whether or not a node should be an external node, you shouldn't really just use the children.length. That's something we spoke about last time, actually. What you should really use instead will be the NOC counter, number of children, right? To see why, you have to look at the lecture from Tuesday, right? If you still got trouble understanding it, you can let me know. We can go over it again. All right, so height will be exercise fee. And let's see, the last example we did, okay, there we go. So we talk about the recursive structure for binary tree, which is like a special case for general tree. You got left subtree, you got right subtree, right? So you only got maximum 2 child nodes from each node. Right, today we're going to speak about some mathematical property for binary tree. We'll get there. That's the final page we spoke about last time, geometrical sequence, especially you want to get a sum. Because in the exam, there will be no data sheets allowed. So in case you forgot about the formula, you should really kind of understand how you can derive the formula in case you need it. So this is a general formula right here, initial term, common factor, the number of terms. And in the case of binary tree, as we'll see, because each node maximum can branch out twice. So the common factor, as we'll see, is simply just 2 for binary. And then the very initial node that we are counting over here is the root, which is always 1 at level 0. So that's why we got 1 here. So when you got r equal to 2 and I equals 1, and then you can simplify this particular formula here just to 2 to the power of k minus 1. Right? So that's really the last bit that we spoke about on Tuesday. Okay? We're going to use this formula many times today when we try to derive the mathematical properties of binary tree. Right? I'm going to keep reminding you about this formula here. And very often, the k over here will just correspond to the tree, correspond to the height of the tree that we're considering. Right? That's typically the use case for the k. All right, any question? All right, that's a recap. And let's now do one warm-up exercise very quickly, and then we'll move on to properties. So this one here, I just want to give you guys a little bit more idea about how you can think recursively on the tree. Last time, we spoke about how you can count the number of nodes on a general tree. And to really count the number of nodes on a binary tree, it will just be the same. You will just count the root and also the subtree one by one. Right? For that one, you can refer to maybe Tuesday's lecture and see how you can do this exercise over here for binary tree. For that one, I'll leave that to you. I want to talk about different exercise. Okay? Let's say we want to search for a particular item in the tree. Okay? For simplicity, I'm just going to write out the method first. It's going to be a Boolean method. You're going to return a Boolean. For example, if I say I want to search, I'll give you 2 use cases. And the first input is going to be the root of some subtree. For simplicity, I'm just going to refer to the name of the node right here. For example, if I refer to A, I'm talking about this particular node reference. Okay? Let's say I'm going to start from A, the root. And I want to search for some data elements. And when I put the letter into the crow, I really meant that data element that's being stored in the tree. Right? So when you do the assignment, of course, things will be 100% precise. For now, just for conceptual sketch. Let's say I want to search for letter G and also letter Z. Right? Apparently G exists. Z doesn't exist. So I can expect the method should really return true for searching for G. That should return false for searching for Z. Right? That's a very easy definition for the search method. What we want to see is how we can define this search method recursively, right? It's going to return a Boolean. Whenever you want to define recursion on binary tree, you just got to do something about the root and then call recursion on the left subtree and call the recursion on the right subtree. It's a very simple pattern. Of course, depending on the problem itself, you may have to make the recursive call a little bit differently. Okay? Let's see for this one here. So it goes like this. First of all, I'm going to check to see if the root I'm looking for already stored the elements I'm searching. A, for example, is not matching G, so it's not here. But it might be in the left subtree, or it might be in the right subtree, either way. But I want to give you a little bit look ahead. So right now, we don't really impose any property in the tree itself. So when we want to search, let's say A here is not containing the element we're searching for, let's say G. So we should really go for left subtree and right subtree. If the element exists in either one, we should really return true, right? But later on, we're going to impose some property on the tree so that we can only go to a particular subtree. It's something called binary search, but we'll get to. Right? That's why I want to do this example here, and then we can compare. Because A does not contain the G we are looking for, so what I will do is I'm going to go for the left subtree over here. Okay, so here I can say search on the left subtree of A. And I can also try to search on the right subtree of A. Search on the right subtree of A. And over here, I want to do the recursive call because A does not match, or you can say not equal to. The A here, not equal to the G I'm searching for. So that's why I got to go to either left subtree or right subtree. I want to see if either one contains the element I'm looking for. That's really what you got to do recursively. Keep going until you reach the point that you know that maybe the element doesn't exist or you find the element, either way. But let's now do a little bit pseudocode, which I normally don't do because it's not really precise enough. But for this purpose here, it's okay. Let's now try to do a little bit pseudocode. Okay. So what I want to do is I want to write the definition for search. If I say I want to search starting from some root n of some subtree, and n here can just be the root over here, right? You can think about this might be just n. And then I'm looking for some elements, okay? So let me annotate that for you. You can think about this will be some tree node. And the E over here will be some data elements that I'm looking for. Right? I want to see if the element exists in the subtree rooted at n. So what I should do is I can say if n already contains the element that matches E, I'm done. Return true right away. Right? If n dot elements, we can say get element, right? Let's now do, again, it's pseudocode. So let's be a little bit less precise. Dot equals E. I have found it. I can say return true right away. That's a special case, basically, right? Otherwise, it's not equal to it. So what I should do is I should really go for here, and then I should really go for here for each subtree, right? There are different ways you can do this. You can maybe check to see whether A is external. If A is already external, we know that, well, let's say, for example, if we are here, if that's the node we are looking at, J here, if it's not equal to E, not the one we're looking for, should we bother to go for left subtree and right subtree? Not really, because there's no such thing. That would be the base case we have to return, right? So there are different ways for you to do that. I'll just show you one way. You can say something like, you can say if n dot left not equal to null, all right? And then you can say return the search on n dot left and then the same element E. Right? That's one possibility. I want to check to see if it exists on the left subtree. And then I'm going to continue from here. I can say if n dot right not equal to null, and then I can say return the search n dot right E. Right? That's another possibility. So think about the order. I got here number 1, number 2, and number 3. What if I have not returned just yet? That means the element is not equal. And then somehow I don't have the left, I don't have the right. What does that mean? That means I'm reaching a node where it's external, and that one does not contain the element I'm searching for. In that case, I can just return false. Right? So number 4 would be just return false. Okay, it's because n is external, no child. Also, n the elements does not match the E we're looking for, right? So that's more like a conceptual sketch. But you can feel free to reorganize the structure a little bit, use the if then else, whatever. But that's okay. But logic is over here. You got 4 different cases to consider, right? 2 and 3 are recursive calls. 1 and 4 are the cases where you know that you can return either true or false. Okay. Any questions on this? Diego.
Could we also try to do the recursive calls using, for example, the OR operator to
Yeah, exactly. So if you want to somehow combine maybe the left subtree, right subtree result recursive call, like a split array, for example, absolutely. That'll be another way to solve it. Give it a try, for sure. I think the way I kind of wrote the pseudocode in the morning session is a little bit closer to that, but they're both okay. It's more like a sketch, so I would encourage you to also try to put it in the actual Java to see which one works. I think both should work. Yeah, there might be some minor detail you have to adjust, but I think the idea is really here. Okay. All right, if no more question, guys, from now on, it's going to be, just before that, go ahead.
So just one more question. If you have if statements like this and you have a return statement, let's say what we're looking for is in the right branch, and we check the if statement from the left one. Won't it never check the right one because we have if and then we return?
Yes, exactly. So we're asking this. If the A here, okay, if A does not contain the element we're looking for, then we try the left subtree first. If the left subtree contains that, we're done because we have found it. If the left subtree somehow does not contain it, then we have to somehow do that, right? Try the right subtree, exactly. Okay. Of course, as I said, maybe that's something you have to go a little bit more careful because when you return over here, it could be true or false, right? So you also got to be sure to check the value. Okay. What you can do is you can capture the value, maybe search the result from over here, and then try to check to see whether it's true or false. If it is true, you're done. You can return. If it is false, you got to return from the right as well. Yeah, there was a minor detail you got to fix. Yeah, absolutely. Very good. Any follow-up? All right. So from now on, it's going to be a little bit more math. Okay, we're going to see some practical property for binary tree. Let's now take a look. But now for the slides, I'm going to start from slide number 28. Okay, that's what we'll do. I'll go very slowly for the very first page. This first illustration from scratch is going to be the most important one that we need to understand for all the others for this for today. So we're going to talk about how the binary tree can be understood for its structure and also number of nodes. What's the maximum? Okay. Before that, let me remind you very quickly about the formula, right? As I said earlier, as we tried to derive on Tuesday, you can see we got this general form, and so we got a special form. I'm going to remind you both. Okay, I'm going to write it here. Okay, let's remind ourselves the general formula about geometrical sequence sum Sk will be, if you got the initial term I, multiplied by r to the power of k minus 1. Divided by r minus 1. That's general form. But for binary tree, what we have is this one here. I will be 1, r will be 2, 2 to the power of k minus 1, 2 minus 1, which will be 2 to the power of k minus 1. So this is going to be the formula we're going to use more. All right? And the k over here typically will be the heights of the tree, that as we'll see. Okay? This will be the heights of the tree. Okay? And let's now try to look at the structure. I'm going to present 3 different columns. The first column here will be the binary tree structure. Okay, that's going to be the first column. That's going to be more visual. And then we're going to look at different levels. And if you guys recall, the way we're going to divide the tree nodes into level is by their depth, right? About how many edges you will take from the particular node all the way to the root. So the question mark over here is really the D for each node, okay, in that particular level. And the third column is something we got to figure out. Maximum number of nodes at that particular level. So the maximum number of nodes at that particular level. Question mark. Okay. Over here. All right. Let's now go one by one. Let's start top down. So we start with the root of the binary tree. There's only a single root, obviously. And then let me just write a root over here. And we know that it's level 0 because the depth for the root will be the number of edges for the root to go to itself, which is 0 by definition. That's why it's 0. How many nodes maximum can we get in this level? Always 1, just the root. All right, guys, please don't get confused. This is a node. This is 0. All right, they're different, just in case you are confused. Okay, that's level 0. Let's get to level 1. When I get to level 1, that means all the nodes at this level here has 1 edge to reach the root. What's the maximum number of such nodes can be there? Only 2, right? Because the way you can branch out will be maximum 2 from the root. So you may branch out over here, and also you may branch out over here. Okay, so I'm going to put 2 right here. Let's do one more, okay? And if I talk about level number 2, level number 2 simply means all the nodes at this level here is going to take 2 edges to get to the root. How many maximum? 4, okay, that's obvious because, for example, you can see every node in level 1 is going to branch out maximum 2 times. So we just do the maximum branching out. So I got 1 here, I got 1 here, I got 1 here, and I got 1 here. All right, exactly 4. And of course, we cannot really just go forever. We have to observe the pattern and predict what's going to happen. And in reality, the tree you're given can be arbitrarily deep. So that's why you cannot just keep doing example like this. You got to observe the pattern. So I'm going to say ... All right, like that. And as you guys can observe, right, as a software engineer or maybe as a computer scientist, when you get to this point, you ought to look at these numbers to see if there's any pattern you can observe. That's what you should do. Once you observe the pattern, you will be able to predict when the tree is arbitrarily deep. All right? I'm going to tell you the pattern right away, okay? But you can convince yourself maybe after class. 1 here is 2 to the power of 0. And the 2 here is 2 to the power of 1. And this one here is 2 to the power of 2. As you can see, the exponent over here just match the level. The exponent here just matches the level. Exponent here just match the level, or the depth of all those nodes in that particular level. That's a very important pattern to observe. Once we know that pattern there, we will be able to somehow predict the number of nodes maximum at every level. Right? Let's do one more thing. Okay. And let me introduce another commonly used variable called h. Okay. So let me start from the root right here. And then I will go all the way to how deep the tree can be. Let's say you can go all the way, let me go a little bit shallower. Okay. How about this? How about here? All right. We call it h. H over here is going to be the maximum depth of the nodes in the tree. Meaning that if I tell you this is the deepest node I can get at the bottom level for the tree, I'm telling you it will take this particular node 1, 2, all the way to the root. So if you try to count the number of edges, 1, 2, 1, 2, 3, all the way, if I sum up all the number of edges together, I'm going to get exactly h. That's a maximum depth I can get from the node in this entire tree. That's the very definition for something called height. Okay, let me write it down. It's a very important transition we are making here. So if you think about counting all the edges over here, 1, 2, 3, all the way to right here. So these are the maximum number of edges to reach to the root. And that one is the very definition of H. It's called the heights. Let me say that one more time. Somehow there should be a bottom of the tree. It cannot be infinite. So I'm saying that the deepest node I have in the tree is going to take exactly H edges to really get to the root. And that will define the height of the tree being H. All right? Guys, make sure you understand this point, right? It's really important. Otherwise, you might be thinking, why do you suddenly have H out of nowhere? Well, I'm just looking at the bottom level of the tree and then try to see how many edges it will take for the bottom node all the way go up to the root. I will say H edges. That's a very definition for the height of the tree. All right? As you understand this, let's now make the tree a little bit more, look a little bit more like a tree. Okay? So I'm just going to draw this. Okay, like that. That's the tree we have, right? That's how high it is. And this guy here, the deepest node, I'm just going to highlight it. Okay? That one there exists at the bottom level. Right here. This one here, what should be the level? Because now I identify this will be the bottom level here, so I should really go to this entry here. What should be the level? H, because level here corresponds to the depth of this node, which should be the height. Right? You can see everything gets connected. All right? So here, I'm just going to put H. And how many nodes in maximum can we get? 2 to the H, because we observed the pattern before. If I got 2, it'll be 2 to the 2. I got 1, 2 to the 1, right? So now I got H, it will be 2 to the H. Let's do one more. What about second last level? If I got this level here, second last level, it should be H minus 1, all right? And then it'll be 2 to the power of H minus 1, right? And etc. Right, so far what we have been building up here from scratch is a very fundamental exercise for you to also try. We really try to see the structure of a binary tree in the most general sense and how we want to figure out the number of nodes. All the mathematical property we're going to see later somehow relates to this build-up. That's why I want to talk about it first. All right, we're not done yet. All right, so here we know about what's the maximum number of nodes in each level. So here comes the critical question. Okay, I'm going to put it here. The critical question here, which I'm going to put here in the middle, question. What will be the maximum number of nodes in a binary tree with height H? Maximum number of nodes in a binary tree with height H, right? As you can see, the H over here is really the H over here, right? Well, to really get that, we got to sum up the different numbers. We're going to sum them up. Let me just do this. We're going to sum up this number here, this, all the way to these two, right? The sequence, geometrical sequence. I'll write it down here. 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus all the way to 2 to the power of H minus 1. That's the second last level. The final level will be 2 to the power H. All right, and then let's look at our little formula here. We can apply that. All right, it's going to be 2 to the power of K. K here will be the number of turns in the sequence. How many turns do we have in this sequence here? Gotta be right. H plus 1. Okay, that's good. Because we go from 0 all the way to H. If you go from 0 to 10, how many numbers do we have? 11. Right? Always got to be plus 1. All right? So basically go from 0 all the way to H. So that will be H plus 1 minus 1. So this will be the final answer. But to really get there, you have to understand the tree structure very well. Okay. All right, any question about this? Yeah.
Could you say broadly that K is defined by H plus 1?
K over here, H plus 1? No, okay. So thinking this way. So this is just the formula where we got special case where R is 2 and I is 1. So K here can be arbitrary number. I'm just saying in the case of binary tree, usually it will have to do something to do with heights. But we might see sometimes H plus 1, sometimes we might see H. So it really depends. Yeah, we'll see. Okay, very good. Okay, let me see if I missed anything here. Okay, so exercise for you guys to try very quickly. You can try it out after class. What would be the maximum number of nodes in a binary tree from level 0 to level h minus 1? Right? That should be easy. Basically, just disregard the bottom level. But what would that be? Okay. So you guys can try it out. Right? Of course, in the written test, in the exam, I can give you the sum up of, from one level to another, arbitrary. Right? You should just know, write out the sequence, and then apply the formula. Okay. Okay. I think this is pretty much everything I want to say. Guys, any question? Given this nice knowledge here, we're now going to apply this one here into distinguishing two kinds of binary tree, right? For that one there, we have to use this result over here. And this will, and also to really distinguish between these two kinds of tree, which I'm going to talk about, is a very nice way to clarify many things. But let's see. Okay. I'll go over the slide as well with you. I think the best way to really explain will be, I'm going to go over with you for each one of them some example to illustrate the definition, and then I'll generalize the definition, and then we'll figure out some property. And then we'll do that for complete binary tree, the first term, and also full binary tree, which will be right here. We're going to talk about these two. They're closely related. So the way I'm going to explain will be visual, which is going to be effective. However, in the test, you may not be presented exactly like this diagram. You will be given like a textual form of the definition, which we're going to see in the slides. But I'm going to help you understand what exactly the definition is trying to say. Right, let's go side by side. So for the slides, you have to go to slide number, give me one moment. So this is something we just discussed. Oh, complete binary tree, right? Slide number 29. Okay, let's start with a complete binary tree. Okay. Before that, let me prepare you for that. Let's now look at this particular tree over here. And when I say the height is equal to 3, hopefully that makes sense to you, right? What's the maximum depth of the node? For example, it will be h, which takes 1, 2, and 3 edges. So that's why h is 3. And let's now try to divide the nodes into different levels. So I can say, for example, this one here will be when the depth is equal to 0. And this one here is when the depth is equal to 1. And this one here is when the depth is equal to 2. And this one here is when the depth is equal to 3. That's pretty good. That's something we did earlier. But now I'm going to further divide the nodes into 3 different areas. Okay? Let me start with the bottom over here. Bottom here, d is equal to 3, but more generally, the 3 here just correspond to the heights. All right? So you can see the 3 here just correspond to the heights. So I would say this is really level h, which we saw earlier anyway. Okay? And this number here is really h minus 1. 3 minus 1, which is 2. Right? And then I'm going to say all the rest above. So these are the levels which I will call less than or equal to h minus 2. So this is like h minus 2 and onwards. It's just decreasing its depth all the way to 0, to the root, right? So I'm subdividing the nodes into level h minus 1, and all the levels that's less than or equal to h minus 2. That's what I need in order to define what a complete binary tree is. That's what you will see in the definition as well. Okay? So what you can try later is, after we have gone through this example here, you can try to make yourself another binary tree that's complete, maybe of height 4. And then you can try to divide again, right, to see how you can understand the definition. But I think this one is enough to introduce the definition. So now we have done enough preparation. Let's now go back to this definition here. And a binary tree will be complete if, given the height h, of course. Okay, right here. So the definition contains 3 parts. We're going to look at each part separately. Part number 1. The nodes with depth h minus 2 has 2 children. All right? So when we say depth h less than or equal to h minus 2, we are really talking about this area here. So all these nodes have the level h less than or equal to h minus 2. All the nodes over here has exactly 2 children. For example, this node here has 2 children. This node here has 2 children. This node here also has 2 children. Exactly 2. That's a maximum you can get. All right? That's part 1 for the definition. And then part 2. The nodes with depth or at level h minus 1, they may have either 0 or 1 or 2 child nodes. May not be 2. Can be 0, can be 1, can be 2. So let's go to h minus 1. H minus 1 is right here. This node here has 2 children. This node here has only 1. And these 2 nodes have no children, 0. So you can see that's exactly the definition, right? That's part 2. Part 3. Okay, before I talk about part 3, just before that, I'll help you a little bit. Okay, so before the part 3, so there are two different ways that you can refer to the nodes at the bottom level. I'm going to write it down, and then I'll talk about part 3. So I'm going to just isolate these nodes over here. Either you can say these are the nodes with the depth being equal to h. That's obvious, right? That's at the bottom level. Another way to refer to them, which you will see in the definition part 3. So these are the children of the nodes at level h minus 1. For example, this node here is the child node of this one here, which exists in level h minus 1. Similarly, this node here is a child node of this node, which exists in h minus 1, etc. Okay? So these are the children of nodes at level h minus 1. Or you can say with depth h minus 1, right? They're talking about the same thing. All right, let me now talk about definition. Part 3. Children of the nodes with depth h minus 1 are filled from left to right. Right, this one you can see that visually. Okay? So the children of the nodes at level h minus 1, so these are the children, right? They should be filled out from left to right. So for h and I, left child and right child. And j here, if there's a complete binary tree, j here must be a left. If j is a right, we're not really filling out from left to right. We're not really doing that, right? So the j here must be a left child. Okay? It must be a left child right here. That's basically part 3 of the definition. Okay? Are we okay so far about definition, right? All right, let's now try to generalize it, the complete binary tree. Okay? Once we, this part here is going to generalize the structure of the complete binary tree. And once we have done that, we're going to figure out what will be the minimum number of nodes and what will be the maximum number of nodes in the complete binary tree, right? So there will be a range of nodes you may have. Okay, let me explain that. So here we got the tree of height h. Okay, and I haven't really drawn the level h just yet. It should be here, but I'm going to talk about it in just one moment. I only draw the tree up to level h minus 1. Okay? So you can think about here is really h minus 1 right here. Right? That's h minus 1. And of course, if you go a little bit down, it's going to be h minus 2. That's why I got this high here, h minus 2, right? And in order for that to be a binary, complete binary tree, by definition, the nodes at level h minus 1 may have 0, 1, or 2 children. Remember, right? That's part 2 of the definition. Now, in order for me to make this a complete binary tree of height h, what's the minimum number of nodes that I should really put in this level here? Can I just put 0? I cannot. Because if I didn't really have any nodes in this level, then the whole tree is not of height h anymore. It's actually h minus 1. So I should put at least 1 node. All right? If I put just 1 node right here, imagine that this is the leftmost node at h minus 1 level. If I just put 1, this will be the simplest way to really make the whole tree complete. Because now I'm satisfying the definition. Now, at, all the nodes at h minus 1 has either 0, 1, or 2 children. This node here has exactly 1. All the others have 0 children. I'm also filling up from left to right, so I'm satisfying it. That's the minimum. What about maximum? Maximum simply means all the nodes at h minus 1 is going to have exactly 2 children. Right? In that case, for example, this one is going to get 2, this one is going to get 2. I'm going to fill this out all the way. Okay? So I can now try to fill it out in level h. So think about in level h, right? This will be h. The purple one there is the minimum. I'm going to put just 1 node. And the pink one is going to be all the way filled out completely to the rightmost. That will be the maximum case. All right? So now we're going to think about what's the minimum, what's the maximum. Okay? But in both cases, thinking this way. If I want to know what's the minimum number of nodes, it's going to be the number of nodes in this tree over here plus 1. Maximum will be the number of nodes in the same tree over here plus the bottom level, which we know is 2 to the h. Right? That's what we said earlier. So these are the 2 additions we got to compare. All right? I'm going to write it down, and then we'll see again. And this one here is going to be the common part, which I'm going to write down first. It will be 2 to the 0 plus 2 to the 1 all the way to 2 to the h minus 1, right? Because I'm going only down to h minus 1. And for the maximum, I also need this part as well. 2 to the 0, 2 to the 1, all the way to 2 to the h minus 1. Right? That's a common part. For the minimum case, I only need to add 1 node right here, plus 1. For the maximum case, I'm going to have all the nodes in level h minus 1 having exactly 2 children. And what's the maximum number of nodes in this level here, h? 2 to the h. Right? If you look at the previous page, that's exactly 2 to the h. So that will be plus 2 to the h. All right? But that's only derivation process. We're going to simplify the number. We cannot just give this number, right? So I would suggest we do 1 by 1 here. Let's now start with this one here. What is this? It's a geometrical sequence. Let me remind you again. Sk is 2 to the k minus 1, right? So this will be basically 2 to the k minus 1. What's k here? H? Agree? Okay. Guys, very good, because you can see that we got 0 all the way to h minus 1. So it should be h. All right? Very good. Okay. So I'm just going to erase this. It's going to be h. And then plus 1. And when I say that one plus 1, I'm just going to get 2 to the h. That's the minimum number of nodes in a complete binary tree with height h. So that's the first number we need to see. And you will see that number in the slide anyway. I'm just showing you exactly how to derive that. And then what about this one here? This one here is just a new sequence, right? The number of turns just plus 1. Okay. So go from 0 all the way to h. We got h plus 1 turn, right? So now that one there, overall, oh, let me use a different color. That one there is just going to be 2 to the power of, I go from 0 all the way to h. h plus 1. And then, don't forget, minus 1. So that's the second number. Okay, we got a first number here. We got a second number here. All right, so these are the two. Question? Yeah? Yeah? Exactly. Exactly. Now we're constrained by mainly the h over here. If you got all the nodes at this level here, simply just have 0 children. If that's the case, then the heights of the tree will not be h anymore. We are constrained by the fact that we want to have a height h tree. That's why. Okay? Good question. You guys got similar, actually deep question like from the morning, which I like. Go ahead.
Why can't we have, for minimum number of nodes in a tree of height h,
Uh-huh.
why can't we take every node to just have one child?
That would be the minimum. That would not be. Because the minimum here is just 1, right? So let's say what you're suggesting is, if you say maybe this node here, also you cannot do that. It will not be complete anymore. I'll tell you why. Let's say this node here, you got 1 child. Let's say left child. This node here, doesn't matter if you got left child or right child. It's not complete anymore. Remember the definition part 3? You got to fill from left to right. It's not left to right anymore, because you're lacking 1 from this right here. So it's not complete. Okay, let me write it down here. Okay, it's a good question here. So what your fellow student is suggesting is like this. So if I got the heights right here, h, and then here, let's say I got this one here, which has a left child. Okay, and let's say I got another node here. Let's say that one there is also left child. This is already not a complete binary tree. It's not from left to right because you have some gap right here, which should be filled out, but you don't have it. All right, good. I'm glad you asked. Okay, so this one here, not complete anymore. Go ahead.
Then what if we take from the start is just one single child continuously, like suppose a linked list? Wouldn't that also be a tree though?
It'll be a tree, but it's just not complete binary tree. That's something we'll get to when we talk about like a minimum number of nodes versus a maximum number of nodes. That's something we'll see. But now we're focusing more on a complete binary tree. Okay, good. All right, so now let's now talk about another one called full binary tree. That one there is more like a special case for complete binary tree. That one there, very simple. We're just saying that every node in the bottom there got to be filled out. All right. So what I will do is I'm just going to say I can extend this level right away and say that it's going to be filled out completely. That means the minimum and maximum, there's no range. They are the same. It's simply going to be 2 to the 0 plus 2 to the 1 plus all the way to 2 to the, for example, h, right? All right, so that one we know pretty well is going to be 2 to the h plus 1 term minus 1. So the definition for full binary tree is very straightforward. So this number here just matches the maximum case for complete binary tree. Okay. Of course, you guys can actually refer to the textual definition on the slides. Let me just do one more visual summary for you, and that'll be good. Of course, you got to digest the details maybe a little bit later. Let's now try to visually summarize about complete versus full binary tree. They are very similar, of course. So we talk about complete binary tree versus full binary tree. Okay. And let's to really compare them, let's assume they are equally tall. Let's say height h. Right here, h. All right. So I'm going to draw one tree over here of height h, and I'm going to draw another one on the right as well. All right, let's now compare them. Okay, all the way down to h minus 1, they look the same, really. So all the way down to here, all the way down to over here, they look just the same, right? Just the same. The only difference is at the bottom level. In the case of the full binary tree, we have no choice. We got to fill it out completely. It's going to be 2 to the h for the bottom level. Okay. Right over here, right here, right? The bottom level. But in the case of the complete binary tree, you have some flexibility. That's why we got minimum and maximum. And over there is going to be basically the number of nodes at the bottom level. The number of nodes at level h can be from either 1, the minimum case, all the way up to 2 to the h. All right? You have some flexibility. Okay, so that's about these two kinds of tree, and we nicely actually apply the maximum nodes comparison that we did earlier. Okay. All right, any question? Kind of interesting, right? I mean, to really see property. And let's now dive even further, even deeper into the tree. All right. And let me give you a roadmap. I want to be in sync with the morning section here, even if I can finish earlier today. But I think I wouldn't go any further. I want to be just the same. Okay. So what we're going to do is we're going to try to look at different measures of the binary tree. So there are 4 different measures, but I'm only going to talk about 2 today. Okay. Let me give you a roadmap. So we're going to talk about what's going to be the minimum and maximum number of nodes in a binary tree. That's something in some way we have seen that already, but we're going to see. Okay. Number of nodes is going to be one measure. And also the height of the tree. This is going to be very important. Whenever we talk about performance of your algorithm, like a recursive algorithm on a tree, the height is really a determining factor about when, if you recursive call just go all the way down to the bottom, how many recursive calls should you make? It really depends on how many levels you got in the tree. So that's really to do with the height. So the height is really important. Okay? Just see one thing very quickly. The maximum height, n minus 1, is like a linear, right? N minus 1. And the minimum is more like a log. If you talk about log versus n, right? There's a huge difference asymptotically. So you rather your tree is getting to more like a log end, okay, for the height. That's something we'll get into a little bit later as well. So we only talk about the number of nodes and also the heights today. On Tuesday, I'm going to also talk about another 2, which is not covered in the written test, right? But we'll still talk about it Tuesday, which is about internal nodes and external nodes. All right, let's now go for the first 2. How do we bound the number of nodes in the tree given some height h? So we have a binary tree, we have some height h, we want to see the number of nodes. What's the minimum, what's the maximum? Okay. And let's say this, we got h being equal to 3. Okay. In some ways, it's more like a drawing challenge. When I say h is equal to 3, what do I really mean? I mean that the bottom node you have, the bottom, or the maximum, how about this? The maximum depth is 3. How do I somehow visualize a maximum depth of 3? That means 3 edges to go from the bottom all the way to the root. If I got my root right here, and then I got the bottom over here, there should be exactly 3 edges to go there, right? I can go for edge number 1, I can go for edge number 2, and then edge number 3. You got exactly 3 edges. 1, 2, and 3. Another question is, I want to figure out what's the minimum number of nodes in the tree that's going to make height 3. If this is already a valid tree, then I can stop here without adding any more nodes, and that'll be the minimum, right? Is this a valid tree? It is, even though it's ugly, but it's a tree. Because you can see you got a root here, and then you got one child, you got one child, you got one child, and then no child. It's a valid tree. So this will be the minimum number of nodes you can have when you got just a height. And it's something called slanted tree. You just slant it one way, okay? Either to the left or to the right. We can get left, right, okay? That's a minimum. What about maximum? Maximum, we can still start with a slanted tree. So here, here, here. So we got 1, 2, and 3. This we know is a minimum. Can we somehow add some nodes without changing the heights? We want to maintain the height to be h equals 3. I can do that. For example, I can say I can add one node here. It's still a tree of height 3. I'm not adding the maximum depth. I can add another node over here. That's still the same tree with the same heights. And then I can add here. I can add here. I'll just try to branch out as much as I can. So here, 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 2, here, and here. That's a maximum. I simply just try to branch out as much as I can. And then that'll be the maximum number of nodes. And how many do I have? I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And let's verify the formula very quickly, and then we'll generalize it. So you can see here, the height is 3. If I apply this formula here, that's a maximum. If I try 2 to the power of 3 plus 1, and then minus 1. 2 to the power of 4, 16, minus 1, 15. Yeah? So that works. I got exactly 15 nodes right here. That's a maximum. Okay? And let's now try to generalize these two structure, which is not too bad. So when I got a tree of heights h, right here, how many nodes do I have? H or h plus 1? Because here you can see I got 1, 2, 3, 3 edges. Because each edge has the end here and the end here, right? You got to count twice, basically, right? So here you can see 1, 2, 3, and 4. 4 nodes versus 3 edges. So the number of nodes is always 1 more than the number of edges, always. You can easily observe that pattern. So the minimum case will be you actually got the root and then all the way to the button over here. And given that the h is actually height is h, that means the number of nodes will just be h plus 1. 1 plus the number of edges. Maximum number of edges to reach the root. All right, so that's where this h plus 1 comes from. All right. And then what about general case for maximum? Pretty much like what we did earlier. If you got a tree here in general, and we know if the height is simply just h. All right, so what we're going to do is we're just going to sum up all the nodes from 1 all the way to 2 to the h, right? So 2 to the 0 plus 2 to the 1 plus all the way to 2 to the h. It's going to be, well, if you remember sk, it's going to be 2 to the power of k from 0 to h plus 1 minus 1. All right, so that's basically what you will see right here. That's how we bound the number of nodes in a binary tree using height h. All right, any question? Let's now do something kind of the opposite. Rather than bounding the number of nodes, let's bound the number of edges, like a maximum number of edges, like a height. Okay, let's try that. Okay, for this one here, it's going to be more fun because you're going to see eventually we'll get locked. Let's see exactly how that's going to happen. Okay, we'll plug in the numbers in a moment to just show you that it works, but let's use one example here. N is equal to 7. Again, it's more like a drawing challenge, right? Let's say you're only given 7 notes to really spare. Somehow given 7 notes, what would be the way to really give you the maximum height of the tree? Right? So for example, if I start with the first note, root, no choice. If I want to draw the second note, it can only be a child right here. Now, if I want to draw a third note, if I go this way here, in some way I'm wasting it to really grow the height of the tree. Agree? So what I should have done is, first note, second note, I can draw the third note right here to grow the height by 1. I can draw another note to grow the height by 1. So every note I'm drawing, I'm just going to grow the height by 1. All right? So what's going to happen is, if I got 7 notes, I'm just going to get something like this. 1, 2, 3, 4, 5, 6, 7. That's the way to really draw a tree with 7 notes with the maximum heights. Right? And what's the maximum heights? Exactly. So when n is equal to 7, the number of notes, you can see 1, 2, 3, 4, 5, 6, 7. The number of edges will be n minus 1. Right? In this case, the h will just be 7 minus 1, which will be 6. You can see 1, 2, 3. Okay, let me just do a little bit thinner. 1, 2, 3, 4, 5, 6. Okay, just 6. That's exactly n minus 1. Okay, that's what we got. And let's now take a look at this guy here. Before we even try to draw, let's plug in this number here just for now. I kind of choose the number just to be perfect, right? But in general, you may have to deal with some imperfection. Okay. So now the maximum here, log this one here. When n is equal to 7, the maximum should be basically log, and as we mentioned earlier, if I didn't give you the base should be 2. Okay. So log 7 plus 1 minus 1. What is log 8? 3. Minus 1, 2. That tells you if you got 7 notes, the minimum height you can get to will be just 2. How? If I try to draw the tree with minimum height 2, 1 and 2, that means that's it. That's the deepest note I can get to. Now, how can I add more notes to get to 7? Well, basically, you got to branch it out, right? Make sure, branch it out, and branch it out. And you got 1, 2, 3, 4, 5, 6, 7. Exactly. All right? So that will be with the same number. If you look at these two trees, this one here and this one here, they have the same number of nodes. However, the height over here is n minus 1, which is linear. The height over here is somehow log n. So this tree here will be a much better tree for you to perform something recursive. Much, much better. If you try to perform something on here, it will be as if you're doing a linear collection. As if. Okay? That's something we'll get into a little bit more later. All right, let's generalize it, and now I'll derive something for you quickly. Okay? To generalize this, we're going to get a tree right here. Okay? When you get a minimum height, that means you get a maximum number of nodes, basically, with that particular height. That's really some insight. Okay? So minimum height, that means the number of nodes is maximum for that minimum heights. Okay, so if the minimum height is actually h, right here. And what's the maximum number of nodes? That means the tree is full. Right? We talk about full binary tree. Okay? It's a full binary tree. And I'm going to give you the number. Full binary tree, it will be n, it will be equal to, if you do the geometrical sequence sum, right? That's something we did earlier. I'm just going to plug it in here. 2 to the power of h plus 1 minus 1. Right? That's something you can refer to the earlier discussion. But let me start from this. We still haven't seen log just yet, have we? I'm going to show you how the log can appear. I'm going to take that full binary tree number of nodes and try to see what the h is. When the number of nodes is, when the tree is full, it's going to give you the minimum heights. Okay? The height here is really the minimum when the tree is actually full. And let's now derive the log together. So I got n equals 2 to the h plus 1 minus 1. Let's do that slowly. First of all, I want to get h eventually, right? H should be here. But h is not in the exponent. I want to get it down. So why don't we move the minus 1 to here? So that means we got n plus 1 equals 2 to the h plus 1. All right? And then I want to move h plus 1 down. How do I do that? Log, exactly, right? Okay. So I'm going to do basically log n plus 1 equals the log of 2 to the h plus 1, which is h plus 1. All right? Just for your information, whenever you say log 2 to the x, it will just be x. Right? I'm pretty sure you have seen that before. Okay? Which will be just h plus 1. So that's kind of the almost the final answer we can get. So let's say we got this one here, and we got this one here. All you got to do is just one more move the term once more. You can move the plus 1 to the other side. So that means h will just be the log n plus 1 minus 1. So that's exactly what you see as the lower bound. All right? To really get a lower bound, you want to get it inside that. To really get a minimum heights, you want to get a full binary tree. Right? Every level must be completely filled out. And let me just say one more thing about the maximum. Okay, maximum here, of course, you can generalize it by just writing. So if I got n nodes, if I got h1 here, all the way to the bottom here, all right, what's the maximum heights? If you got n nodes, the number of edges will be the maximum, just n minus 1. Right? Always one less. In that way, the h would just be n minus 1. That's a maximum. All right, any question? Yeah, I will start with Josh first.
Can we consider non-integer heights? If you have a non-full binary tree, then that's going to give us a...
Yeah, of course. You know, this in this example here, I simply choose the number so that you can take the log directly, right? Because it's more like a larger than or equal to. So you will take maybe the ceiling of that. Okay. Yeah, that's something you gotta calculate. Yeah.
Same question.
Same question. Good. Yeah. But normally I'll just give you some perfect number. Okay, so you can plug in. If not, you can still figure out what's the ceiling of the integer. Guys, if you don't mind, can we say just take attendance right now, and then we don't take a short break today. I just want to do the traversal quickly. Okay, thank you. If you can get your iClicker now, and then I'm just going to take it. All right, 10 minutes. Let's now talk about traversal. So I'm going to skip the slides a little bit, but tomorrow I will tell you exactly the range of slides you should really study for general tree. Okay, the other two properties is not covered for the written test, but we'll do that on Tuesday. All right, so we're going to go here. I want to go to the slides where we got traversal. Okay, I'll talk about application as well on Tuesday. Okay, traversal. Traversal, by definition, is just a way to systematically visit every node in the tree in different fashion. So there are 3 different ways we can traverse the nodes, okay, which I'm going to show to you one by one. All of them can be done recursively. And so these are just the typical application for traversal, but you guys are going to do that in the assignment anyway. Maybe I can revisit these maybe a little bit later. Okay, so there are 3 traversals. Number 1 is called pre-order traversal. And you just got to remember the principle. Don't memorize the code. Remember the principle. You have to visit the parent first, and then recursively visit all the child subtrees. Parents and then children. That's how I remember it. Okay, I'm going to illustrate to you. That's the pre-order. And then you got over here, okay, that's the code you can look at that, right? You can see that's where the recursive call occur, after you have visited the parents. Post-order, the opposite. You're going to recursively visit all the child nodes, and then you visit the parents. There's a third type, which does not really apply to general tree. If you recall the ADT lecture, we talk about something called precondition, right? So the precondition for in-order traversal is the tree must be binary. Okay, I'm going to leave the code over here. That will be some exercise you can try. I can go over again with you maybe on Tuesday, but this one here will be covered, right? Let me focus more on the pre-order and post-order. Once you get those, in order should not be difficult. All right, let's now talk about pre-order, pre-order, post-order. I'm going to put it side by side, okay? And for pre-order here, let's now try that. Let's say I want to do pre-order on the tree rooted at David. Remember, parents and then children. So what I will do is, I'm going to first of all visit David. And then I'm going to put David here right away. And then I'm going to recursively visit each child from left to right. I'm going to recursively pre-order traverse this tree, but as a base case, only one node. So you can think about this one here is about pre-order of Ernesto, which will be just Ernesto. And then I'm going to do pre-order traversal on the second child, which will be Quiz right here. That one there is going to be a big sequence right here. It's going to be the pre-order of Quiz. So far so good? All right, you can see the structure here, right? Now, in order for me to do pre-order of Quiz, again, parents followed by children. So I will do Quiz first. And then I'm going to do pre-order traversal on the tree of the first child. And then pre-order traversal of the second child. So it's going to be one sequence here that's larger and one sequence right here. So that one there is going to be pre-order of the second child, Anna. So that will be just Anna. Right? And then what about the pre-order of this particular tree? I'm going to do parents and then children. So I'm just going to say, first of all, I'm going to put Elsa right here, the parents. And then I'm going to pre-order Shirley, pre-order Vanessa, and also pre-order Peter. All three of them are base cases. So I'm going to get one here, and one here. So I got Shirley, Vanessa, and Peter. So you can see each horizontal line represents a recursive call you have to make. Okay? So what's the final order? The final order would be David, Ernesto, Chris, Elsa, Shirley, Vanessa, Peter, and Anna. Pre-order. All right? You can think about it. There will be some exercise for you in the new page, which I will go over on Tuesday. Post-order. We're going to reverse the recursive call. Right? Post-order means we're going to look at the child first and then the parents. Okay, let's now start with that. So I'm just going to say, first of all, David is going to be put last. Right here. That's his parents. And then I'm actually going to, first of all, put the post-order traversal of the first child. You can think about that one there is going to be the post-order of the first child, Ernesto. So this one's base case. I can put Ernesto here. And then I'm going to do the post-order of the second child, Quiz. Right here. All right, so that one there is going to be a big sequence here until the end, up to David. Post-order of Quiz. So now let's see the general structure here if you compare. Before we got David here at the first, here we got David at the last, right? That's exactly the difference between pre-order, post-order. How about this one, post-order Quiz? Quiz, the parent is going to be put at last. So I'm going to put Quiz right here. And then I'm going to do the post-order for Elsa right here. Okay? And then post-order for Elsa right here. Post-order for Elsa. And then the post-order for Anna. Post-order for Anna, which will be just Anna. All right. Now, what about post-order for Elsa? Basically, I got to put Elsa first. Well, actually, Elsa last. It's a post-order. So I'm going to put Elsa right here. And then post-order on Shirley, post-order on Vanessa, and also post-order on Peter. So I'm going to get 1, 2, 3 here. Shirley, Vanessa, and Peter. So what's the ultimate outcome? It's basically going to be Ernesto, Shirley, Vanessa, Peter, Elsa, Anna, Chris, and David. Different sequence. Right, get yourself familiar with this. All right, the final thing. I got 3 minutes, okay? This will be something I want you to practice as well. You can download the template later, but I'm going to show to you this will be the kind of smoothness you want to develop before the written test. All right? Now I'm given this particular tree, and we want to do pre-order, in-order, post-order. I'm going to leave the in-order for you before Tuesday. I'm going to do it again. Now for pre-order, okay? Of course, you can try to really develop in a way that's going to be like this. That's okay. You're still learning. But this will be the speed you want to develop. Something like that. Pre-order minus divide, multiply, plus 3, 1, 3, plus minus 9, 5, 2, plus multiply 3, minus 7, 4, and 6. Okay? And let me do a little bit here. Minus is really here. And this subtree corresponds to from here all the way to here. And this subtree over here corresponds to this part over here. Okay? You can divide further. Okay? Pre-order. How about post-order? For post-order, I'm going to put here. Post-order will be child first, right? 3, 1 plus 3 multiply 9, 5 minus 2 plus divide. I'm done with the left subtree. All right? And then I got 3, 7, 4 minus multiply 6 plus. I'm done with the right subtree. And then minus. So minus here is going to be the minus here. And then the post order on this subtree over here is basically from here all the way to, oh, sorry, too much. How about here? And then finally, we got this part over here. That's going to be this part over here. Okay. I might just miss one thing here. I beg your pardon. This one here will be all the way to the plus. Oh, sorry, all the way to divide. Okay, there we go. I think that's right. And then this one here is going to be here. I think it's also valuable for you to see the correspondence of the different subtree, right? Try to practice this before Tuesday, and then we'll do in-order traversal again. Okay, I will confirm about the coverage tomorrow when I release the example question. All right, see you next week.